Hello students, welcome to ALPHORES e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are about to deal with the session number 104, second year Neet. In this session, I will be starting a new chapter. The chapter name is Magnetism and Matter. So in this chapter, we will study about what magnetism related phenomena. Okay, so let us see what we can start with. So here, let us try to understand what magnetism is. Magnetism is the force exerted by magnets when they attract or repel each other. Magnetism is caused by the motion of electric charges. So, what is magnetism? It is what force exerted by magnets when they attract or repel each other. That's what we call it as magnetism. And what is the main reason for this magnetism? Motion of electric charges. You guys will come to know about how come these moving charges can exert or can create, can produce magnetic field in some other chapter. For time being, you just remember that magnetism is caused by what? Caused by motion of electric charges. Every substance is made up of tiny units called atoms. Each atom has electrons, particles that carry electric charges. Electrons are what? Particles that carry electric charges. Spinning like tops, the electrons circle the nucleus or core of an atom. So this is what happens inside the atom. Electrons, they spin and simultaneously they revolve around the nucleus or the core of the atom. Their movement generates an electric current and causes each electron to act like a microscopic magnet. So here in the first sentence, what did I say? It was said that magnetism is caused by the motion of electric charges. Yes, inside an atom, electrons are revolving in circular paths, isn't it? According to Bohr's model, isn't it? So whatever those moving charges are there around the nucleus, they constitute some amount of electric current associated with them. Already we have seen in current electricity chapter. Okay, we have derived one equation also for what current associated with an electron revolving around the nucleus. So if current is there associated with the electron revolving around the nucleus, it can produce what a magnetic field, and it can act as a microscopic magnet. And how many such kind of microscopic magnets will be there? Depending upon type of atom you are dealing, several electrons will be there, so several microscopic magnets will be there, isn't it? So this is how you can imagine the picture. This is the nucleus, the orbiting electron, it's revolving and it spins. Because of spin motion, there will be some magnetic field. Because of revolutionary motion around the nucleus, there will be some magnetic field. Okay, so if this is the spinning direction, you can talk about north south as well. I'll tell you about what north south are. Okay, so spinning motion contributes to some magnetic moment. I'll tell you what magnetic moment also. Magnetic moment is something which is a characteristic of a presence of magnetic field for a given body. You can, if you are able to calculate magnetic moment for a given body, it means it is a magnet. It is a magnet. So here, a part of magnetic moment for an atom is contributed by spin motion of the electrons. A part of magnetic moment of an atom is contributed by orbital motion of the electrons. So when you add these two things, it gives rise to atomic magnetic moment. Okay, and such kind of atoms will be there, several atoms inside the material. So each atom, now you have come to know that each atom actually behaves as a tiny magnet. Okay, so all those magnets together forms a larger magnet, a bigger one, right? Okay, so the origin of a magnetic nature or the magnetism or magnetic property is where its origin is deep inside the atom for any material. If you take magnet, that magnet contains several atoms in it. Okay, inside the atom, this is how a magnetic field is originating, and that's how it is summing up on larger scale when you are dealing with the material. Okay, so let us talk about this a bit more. Just a moment. Okay, let us talk about type of magnets. We have two types: natural magnets, artificial magnets. The magnet which is found in nature is called as natural magnet. Usually magnetite, Magnetite ore is called as what a natural magnet. It is the main source for iron. Okay, so magnetite is what a naturally available magnet. Okay, so the magnet which is found in nature is called a natural magnet. And artificial magnet, man-made magnets. The magnets which are artificially prepared are known as artificial magnets. Okay, in refrigerator we use magnets. Okay, so neodymium magnets, refrigerator magnets, these are artificial magnets. Okay, artificial magnets are prepared from steel, nickel, iron. From those things only we prepare artificial magnets. Okay, so magnets, these are the magnets that you might have seen. Speaker, you know, a speaker contains a magnet of this shape, circular shape. Okay, so properties of magnets. Attractive property. See here, if this is a magnet, if this magnet is brought to this close to this metal, what is happening? This metal is attracted towards this magnet, isn't it? See again. So this is a magnet. So basically, magnet has attractive property. It attracts magnetic materials, iron, nickel, cobalt, such kind of things. Okay, right. You can also think about the other kind of possibility. I will show you just a moment. This one. See here, one magnet is placed inside a small glass chamber. Glass is not a magnetic material, and there are tiny magnets are there, small magnets. When this bar magnet is brought close to this one, tiny magnets are responding. See, they are oscillating. Now what was done? This case is opened and bar magnet is placed inside, and all those tiny magnets are aligned in a specific order. There is a fashion. In a specific fashion, all these tiny magnets are orienting. What is that? See children, around a magnet there will be a magnetic field like this. Magnetic field lines, these are called as magnetic field lines. These field lines starts from North Pole and they end at South Pole. Okay, so in whatever fashion these magnetic field lines are aligning, around this magnet, the same fashion here, if you observe, all those tiny magnets are getting aligned. See, once the magnet is placed here, okay, along the field line direction, see, from here to north to south, whatever fashion you will see, whatever kind of field lines you will see, similarly here also, field lines or tiny magnets are getting aligned. They are getting aligned along the field lines, isn't it? Now once again, have a look at this one. Tiny magnet is placed inside this. Now all the tiny bar magnet, once it is placed inside, the tiny magnets were aligned, according to the field lines arrangement. Okay. So directive property. Let us talk about this directive property. Directive property in the sense, if you suspend a magnet like this to a retard stand, okay, wooden retard stand, because you are not supposed to take metal, metal will have affinity to get attracted towards magnet, right? So we have taken a insulating retard stand which is made up of wood, and it is suspended like this. When it is suspended, the north pole of the magnet points always geographic north. See here, when compass is taken, in the compass the needle is showing geographic north, and along the same direction north pole is aligning, and this is south pole. Okay, it doesn't matter if you oscillate this magnet and if you disturb this magnet like anything, again it gets aligned along the same direction. So this is what we call it as directive property. Okay, maintaining a specific direction. If a bar magnet is suspended, the nature of if a bar magnet is maintaining a specific direction, then what you can call it as, you can call it as a directive property. Okay, directive property. So like this, another thing is, like unlike poles, south pole and north pole, they attract each other. Opposite poles, they attract each other. And like poles, south they repel each other, north they repel each other. All these things, they fall under the category of properties of magnets. Attractive property, directive property. In case of attractive property, this is what you can study about. Opposite poles attract each other, like poles repel each other. And one more property is, magnetic monopoles does not exist. A single north pole, a single south pole does not exist. You may think that, sir, here one bar magnet is present, I will cut it up to here, then this will be North Pole, this will be South Pole. No guys, that is not possible. Once you cut it here, okay, whatever piece you will be having, again that possesses two poles, North and South poles. Okay, so you cannot create a magnetic monopoles. Okay, magnetic axis and magnetic meridian. So all that we were trying to do is we were trying to understand fundamental details connected with the magnet. So here magnetic axis, what is magnetic axis, what is magnetic meridian? Let us try to understand. I have taken a magnet. This is north pole of the magnet, this is south pole of the magnet. Okay, and this magnet, let us say it is freely suspended. Like in the previous slide, it is freely suspended. A string is taken, it is tied at the center and it is suspended to a wooden retard stand. You can imagine like that. Now, whatever line is there, this line passing through the north and south poles, that line is called as magnetic axis. That is called as magnetic axis. Magnetic meridian in the sense, a plane that is passing through the magnet like this, a vertical plane passing through the magnet, that is called as magnetic meridian, vertical plane. Okay, vertical plane. Now, let us try to understand a few other details, parameters connected with the magnet, bar magnet. I'll consider a bar magnet and I'll try to understand what geometrical length and what magnetic length. Geometric length in the sense, the actual length of the magnet is called as geometric length. I meant to say that if you take a bar magnet and if you measure it with the scale from end to end, you will get this capital L distance. That is what we call it as geometrical length. And that is not magnetic length. The reason is, whatever south poles and north poles we have been talking about, those north poles, they don't lie directly on the cross section of this bar magnet. The north pole will be slightly inside somewhere here. South pole will be slightly somewhere here. And if it comes to the question of magnetic length, what you will take it as magnetic length? The separation between south and north pole will be taken as magnetic length. And what it will be from here to here. Just now I said south pole won't be here on the surface. It will be slightly inside. North pole will be slightly inside. So when you take a distance of separation between those two pole centers, that accounts for our magnetic length. And obviously magnetic length, 2L is smaller than geometric length. Okay, but usually when you take a bar magnet, you will not be able to measure this magnetic length, right? You don't know where this spot, south spot is located inside the magnet, north spot is located inside the magnet. All that you can do is from end to end, you can measure the length. So if you are given a bar magnet and if you are supposed to find out magnetic length, what you can do is you can make use of this equation. Usually magnetic length will be 5/6 of geometric length. Okay, obviously magnetic length is smaller than geometric length, isn't it? So magnetic length is equal to 5/6 of geometric length. Remember students, if you take a semicircular magnet, something like this, the magnetic length will be taken as distance of separation between these two poles, shortest distance. Okay, you are not supposed to take this distance along the arc. Okay, here also what was said, the shortest distance between two poles of a magnet along the axis is called as magnetic length or effective length. And here, what is the shortest distance between south pole and north pole? It is equal to diameter of this semicircular magnet, which is equal to 2r. If r is the radius of this semicircular magnet, 2r is the diameter. Okay, so that's how you are supposed to find out magnetic length. Now, pole strength. Let us try to understand one by one all the parameters connected with the bar magnet. Later we can make use of all these parameters to understand the behavior of a bar magnet. Okay, pole strength. The ability of a pole to attract or repel another pole of a magnet is called pole strength. Sometime before we were talking about attraction between unlike poles, repulsion between two like poles. The ability of a pole to attract or repel, how well a pole can attract, how well a pole can repel. That is what gives us measure of a pole strength. If I say that pole strength is more, that particular pole can repel a magnet more or attract a magnet more. Okay. SI unit of pole strength is ampere meter. Okay, and pole strength is a scalar quantity. It depends on the area of cross section of the pole. So pole strength depends on what? Area of the cross section of the pole. This point is very important. I want you to remember this. Pole strength depends on area of cross section. It means if area of cross section decreases, pole strength decreases. If area of cross section is more, what happens? More field lines will be coming out. So more pole strength will be there, isn't it? Okay, this is how you can more the number of lines here, then we say that south pole strength is more. If more number of lines are present here, north pole strength is more. Okay, so if pole strength is more, they attract rapidly. If pole strength is more, they repel rapidly. Okay, there will be a high degree of repulsion, high degree of attraction if pole strength is more. Next, inductive property. When a magnetic substance such as iron bar is not a magnet, but it is a magnetic substance. Magnetic substance is in the sense it can be magnetized easily. It can be attracted by a bar magnet easily. Okay, remember, iron bar in the sense it's not a magnet. Okay, if you want, you can make a magnet out of that. Okay, when a magnetic substance such as iron bar is kept, magnetic substance is in the sense a substance that can be attracted by a bar magnet. It's called as a magnetic substance. When a magnetic substance such as iron bar is kept very close to a magnet, an opposite pole is induced at the nearer end and a similar pole is induced at the farther end of the magnetic substance. This property is known as inductive property. Okay, so you can magnetize iron bar. Okay, so what was it? If it is kept close to a magnet, an opposite pole is induced at the near end and a similar pole is induced at the farther end, okay, of the magnetic substance. This property is known as inductive property. So that's how you can magnetize. Repulsion is a sure test of magnetism. Repulsion is a sure test of magnetism. For example, if you take a magnet, okay, let us say these pins are what they are magnetic substances. They are not magnets. They are neutral. They are they are not magnetic. They are not magnetized. They are not magnets. They don't have any north pole or south pole. Okay, but they are magnetic substances. So they can be attracted, right? They can be attracted. If at all this is a magnet, this pin is a magnet. Okay, when you bring this bar magnet close to this pin, there can be attraction. There can be repulsion also. If there is a repulsion, what does it mean? This pin is a magnet. This pin is magnetized. That's how you can understand. If this pin is not magnetized, then there will be always attraction between these two, between bar magnet and this pin. Okay, right. So that's what I meant to say. Repulsion is a sure test of magnetism. Like in the case of electrostatics, also repulsion is a sure test of a charging body. Okay, when you can say that a body is charged, you can confirm with the help of repulsive force between another charged body and whatever body you have charged. Okay, magnetic moment. This particular physical quantity is very important. Let us try to understand. Before that, let me define what magnetic dipole is. This magnetic dipole is quite similar to electric dipole. Electric dipole is what it was defined as earlier. Two unlike charges of small magnitude separated by a finite distance. That arrangement is called as electric dipole. Now let us see what a magnetic dipole is. A configuration of two magnetic poles of opposite nature and equal strength separated by a finite distance is called as magnetic dipole. Yeah, magnetic dipole definition and electric dipole definition both sound similar. Configuration of two magnetic poles of opposite nature and equal strength. Both are opposite nature. It means south and north, and both are supposed to have same strength. Separated by a finite distance is called as magnetic dipole. Magnetic dipole moment. The product of pole strength, any pole, you can take any pole, either north pole or south pole, and magnetic length of the magnet is called magnetic dipole moment or simply magnetic moment. So magnetic moment, mathematically it is expressed as m into 2l, and vectorially m bar is equal to 2l bar into m. So magnetic dipole moment is a vector quantity like electric dipole moment. In case of electric dipole moment, how it was written mathematically? Q, charge multiplied with distance of separation or length of the dipole. Distance of separation between the two charges or length of the dipole. Here, m into 2l. There, in case of electric dipole, q into 2l. Okay. So when you compare whatever you are studying here with the electrostatics details, you will be able to understand these things much better and you can remember very easily. So vectorially, it can be represented as, m bar is equal to 2l bar m. Magnetic moment is a vector whose direction is along the axis of the magnet from south to north pole. I want you to recollect direction of electric dipole moment. Electric dipole moment direction is from negative charge to positive charge. And here, direction of magnetic moment is from south pole to north pole. It means whatever south pole we will be dealing here, that is relevant to negative charge in the electrostatics. Whatever north pole we will be dealing here, that is equal to positive charge in electrostatics. I want you to remember like this. The SI unit of magnetic moment is ampere meter square. The dimensional formula is AL square, ampere meter square. Okay, because pole strength units are ampere meter, and length its units are meter. So ampere meter into meter, ampere meter square. Okay, so direction of the magnetic dipole moment will be from south to north, like this. Remember this point, children. Variation of magnetic moments due to cutting of magnets. What do you mean by cutting of magnets? Let us say I have taken one magnet like this. Its pole strength is M. Let us say the magnet is cut 3 times. Here, 1, 2, 3 times it is cut. If we cut 3 times, how many pieces will be generated? Don't think that 3 pieces will be generated. 4 pieces. 4 pieces will be generated. Okay. Okay. So if it is cut 2 times, how many pieces will be generated? 2 pieces will be generated. Like this, if it is cut 3 times, 4 pieces were generated. Now what has happened to the cross-section area of the magnet? It is decreased. Earlier it is, let us say A, now it is A by 4, each individual magnet's cross-section area. Whereas the length of the, this piece is equal to length of the original magnet. So there is no any change in the length, but change in the cross-section area can be observed. If there is a change in cross-section area, it means pole strength will change, because pole strength is something that is directly proportional to area, cross-section area. So now pole strength becomes M by 4. Earlier it was M. Since its cross section was now it's 1/4 of earlier cross section. So pole strength will also be M by 4. So in general, if a magnet is cut n times, n plus 1 pieces will be formed. Remember, children, while you will face problems based on this one, you will face 2 different kinds of problems. He will say that a magnet is cut into 4 pieces, or a magnet is cut 4 times. If it is cut 4 times, you will have 4 plus 1, 5 pieces. If it is divided into 4 pieces, just take it as 4 only. Okay. Consider a bar magnet of length 2L, pole strength M, and magnetic moment M is equal to 2L into M. When the bar magnet is cut into n equal parts parallel to its length, then, so what was done? N equal parts parallel to its length. Okay, if this is the case, what happens here? Length remains constant. There won't be any change in the length. Whereas cross-section area becomes 1 by n, because it was divided into n pieces parallel to the length. Therefore, pole strength becomes M by N. Therefore, new magnetic dipole moment will be, earlier what was the magnetic dipole moment before it was divided into small pieces? 2L into M. Now 2L into pole strength of individual piece is how much? M by N. So 2L into M is nothing but M. So you will have M by N as new pole strength for each individual piece of magnet. Okay. If the magnet is cut n times, here it is cut into n equal parts. Now what I'm saying that if the magnet is cut n times, if it is cut n times, there will be n plus 1 pieces. If there are n plus 1 pieces, length remains constant. Cross-section area becomes 1 by n plus 1. Therefore, the pole strength is M by n plus 1. Final magnetic dipole moment of individual piece will be 2L into M by n plus 1. Or 2L into M is nothing but M, so M by n plus 1. So the magnetic dipole moment of individual piece becomes 1 by n plus 1 of initial magnetic dipole moment. Now, when the magnet is cut into n equal parts perpendicular to its length, like this, perpendicular to its length, n equal parts. Area of cross section, see here, earlier whatever area is there for each piece, now area of cross section remains constant, but length is different. Since area is constant, pole strength will be constant, whereas length of each part becomes 2L by n. Earlier length is 2L, now it is 2L by n. So magnetic dipole moment M dash is equal to 2L by n into M. 2L into M is nothing but M, so M by n. If the magnet is cut n times, you will have n plus 1 pieces, isn't it? Corresponding equation will be this one. Okay. When the magnet is cut into x equal parts parallel to its length and y equal parts perpendicular to its length. So x parts along this direction, y parts along this direction. It means now cross-section area is changed, length also changed. Length of each part becomes 2L by y because it is divided into y parts along the length. Pole strength of each part becomes M by x because along the length it is divided into x parts. So each this particular portions, what the pole strength becomes M by x. Therefore, new magnetic dipole moment will be M dash is equal to 2L by y into M by x. 2L by y. This is the new length of individual magnet. You consider this small piece. This small piece length is 2L by y. And this small piece pole strength is M by x. So 2L into M is nothing but M. The total magnetic dipole moment of a piece magnet before it is divided into x and y parts. So in the denominator you will have xy. That's how you can deal with the cutting a magnet, and you can talk about magnetic dipole moment of each individual piece. This is where I will close the session, and in the next coming session we'll deal with a few other points connected with the magnetic dipole moment only. Okay, students, thank you.